Good evening, everybody. My name is Professor Pat Gyrey. It's my great honour to be President of the Royal Irish Academy, and it's a great pleasure to welcome you here to Academy House. As a quick show of hands, how many people are here for the very first time? Okay, about a quarter. That's good. What a fantastic meeting room. I bet you didn't know that the only interesting thing on Dawson Street was not Café on Seine, but actually what's opposite Café on Seine is actually even more interesting. So you're very welcome, and yes, this is a fantastic meeting room. So the other officers here present are our Executive Director, Dr. Siobhan O'Sullivan, and also the Polite Literature and Antiquities Secretary, Professor Claire Connolly, as well as Dr. Mary Kelly, the Treasurer. So we are all delighted to welcome you to the Royal Irish Academy this evening for tonight's discourse on artificial intelligence and weather forecasting, harnessing AI, the future of weather forecasting. So it's great to see such a big crowd here this evening. Always to be predicted for an Irish audience, because the first thing we always start talking about is the weather. So it's great to see you here. So this is the sixth and unfortunately the final discourse in our 2024-2025 series, which examines artificial intelligence or AI from various perspectives with distinguished speakers who are experts in their various fields. Academy Discourses, just so you know, are the oldest and most renowned series of talks in Ireland. The first discourses were presented in 1786. Historically, they were the occasion reserved for the most distinguished academics to first reveal and discuss their work in public. We now record these discourses and they are available on the Academy's website, www.ria.ie. Before we begin, we have some short Academy business to undertake. The minutes of our last discourse, Responsible AI, Is It Mission Impossible?, which took place on the 24th of April 2025, were posted online. Since our members did not inform us of any issues, and I have to say they still rarely do about these minutes, I've actually taken the opportunity to sign the minute book upstairs, and so that's all that Academy business done and dusted for the evening. So it's my great pleasure to welcome our esteemed speakers for this evening's discourse. First of all, the speaker will be Florian Pappenberger. He's Deputy Director General and leads the Forecasts and Services Department at the European Centre for Medium-Range Weather Forecasts. He was responsible for the 24/7 production of weather forecasts, forecast quality control, verification and diagnostics, the development of novel forecast products, applications of weather forecasts such as flood, drought, fire and health forecasts, numerical weather prediction relevant software development, Copernicus and destination Earth services at that European Centre, data sales and outreach and training. That sounds like a very busy job, Florian, I have to say. How do you have the time for that? And a special welcome, as you'll notice when Florian comes up, unfortunately an accident with a bicycle on Monday, a broken collarbone, and a particular thank you for coming under those circumstances. Well done, and I hope the collarbone holds up for the evening, as they say. In addition, he has led the migration of the operational forecast to a new high-performance computing centre, the establishment of the European Weather Cloud. I'm sure people there had a great chat and talk about that as the name for that. Well done. And is responsible for the machine learning activities at that European centre. So Florian himself has a background in the forecasting of weather-driven natural hazards, including floods, droughts, windstorms, forest fires, and impacts on human health. He has over 10 years of expertise in operational probabilistic forecasting, extreme value statistics, and numerical model system development at that European Centre. He's the author of over 250 scientific publications and has won several scientific awards. He's a Fellow of the Royal Geographical Society and the Royal Meteorological Society, and a member of several other important professional bodies, including HEPEX, the British Hydrological Society, EGU, AGU, EMS and AMS. And I'm sure all the people in the area of meteorology know exactly what those three-letter acronyms stand for. Don't ask me, I would fail that particular exam. Although TLA is the three-letter acronym, I know that particular one, but apart from that, I don't know those four. Apologies. He served on the editorial board of several international journals and regularly advises on international committees, including the WNO, the W Health Organization, and World Bank. Welcome, Florian. And our respondent this evening, and just so you understand what's going to happen, Florian will speak for about 45 minutes, lecture, so to speak, and then the system in the Academy is we have a member or somebody high up in the area of that particular area who responds on behalf of the Academy. So our responding this evening is Conor Sweeney, and he's a lecturer in Applied and Computational Mathematics at the School of Mathematics and Statistics at University College Dublin. Great university, what can I say? His research has a focus on renewable energy meteorology and explores seasonal forecasting, extreme climate events, and the spatio-temporal analysis of atmospheric data. He's also interested in agricultural meteorology and is working on trying to forecast evapotranspiration. That sounds mildly religious, I have to say. He spent a year trying to get a weather pattern analog base code to remove systematic errors from weather forecasts. Unfortunately, he failed, but he was just ahead of the AI curve nonetheless. Conor is Deputy Director of the UCD Earth Institute and has a keen interest in working with people from a range of different disciplines. As President of the Irish Meteorological Society, he's also committed to raising public awareness of the importance of weather forecasting and climate change. Now to the discourse, and Florian, over to you, and I look forward to your presentation.
Thank you very much for having me, and thank you all for being here. What a fantastic room, and what a brilliant occasion, because on the side you actually see the records of weather observations. Many of them actually predate the discourse first date, but it's absolutely fantastic. So if you have time, some minutes later, just have a look over there and look at those weather records, because of course all you know that AI or machine learning needs data. It's extremely data hungry. And if you listen to some of the other discourses, so it was not always obvious where those data were coming from, but here you actually have those records, and those records are available to you. It is an absolute pleasure for me to talk to you about AI and weather forecasting. In a scientific career, you sometimes go through revolutions, but you rarely go through revolutions which are that fundamentally to changing to what you actually do. The European Weather Centre was created in the 70s to do a forecast of things which were very hard to do. Something which we call medium range, so it's 3 to 15 days type of forecasts. So something where we really had to create or had to put resources together, not just human resources, but also computers across Europe to do this really hard job. And this morning I was at Met Erin, which is a fantastic weather service, and was actually part, or is part, of that European Weather Centre. And you see there our member states in blue. We have 3 locations in Reading, Bonn, and Bologna, and it's an absolute pleasure to be here today in Dublin. Yeah, you already said weather forecasting. We like to talk about weather. Weather is not something new. We've done this for decades, hundreds of years, to be really fair. And this is sort of one of the first early applications for that. And when we talk about the evolution of weather forecasting, it's really trying to put equations into a computer. That's how simple it is, and trying to do outputs and then do something with those outputs. So that's sort of the simple theory. And you may know Louis Fry Richardson visionary idea of a forecast factory, which was a small town of scientists and nerds sitting together there and sort of doing these calculations by hand. It's a fantastic illustration. It's actually not far off what we do today. We do model data, we do sort of forecast the world on a grid. And this is similar to the grid he had, just we didn't have humans there, we have small processors there for each of those type of applications. And this hasn't really changed too much in terms of AI or machine learning. This forecast factory, how it was turned, is exactly how we still produce weather forecasts. So as I said, the process is very simple. Well, at least theoretically, it's very simple. We collect a huge amount of observations. We collect 800 million observations a single day. Every single day, we get 800 million observations into our computer of weather across the globe. These are observations from planes. These are observations from ships, from buoys. These are observations like your radar stations here in Ireland, which you have, or even the records which you see over there nowadays very often, of course, automized, which really come in. 800 million, we put them into physical equations onto a big computer. We use humans and brains to write those physical equations. And then we get out a forecast, as you see on the bottom right, which you should be familiar with. It's very similar to what is the one you see on the Met-Area websites. In a way, where are we? This forecast hasn't changed, but it has improved over and over the time. In 1975, oops, why did it change? In 1975, that is me. In 1975, we could forecast a certain variable just about one day. Okay, one day in the future, we could do a forecast which was a good, accurate, okay forecast. 2025 looks slightly different. We got to 6 days. The same variable is 6 days. For the nerds in the audience, it's maximum temperature in Europe, which I've used here as a reference. I could have used other variables. Anyway, so forecast has dramatically improved over the last decades. And what you see in the top right corner is how we represent this Earth. In 1975, this is actually a picture from the 2000 one, to be really fair, you saw how we sort of simulated the Earth in a very coarse grid. You sort of can make out the continent of Africa. You sort of can make out clouds. But you sort of have to put a lot of imagination in there. Okay? If you go to the figure on the right, this is the latest forecast, 4.4 kilometers across the globe. You can see the continent of Africa very crisp. You can even see the clouds very crisp. You can see very beautiful swirling patterns in these clouds. So forecasts have significantly improved in terms of resolution. If I put this into context, and we can sort of, we like statistics, we like measuring, what you see here is what we call a score. I've put the details on the side. It doesn't really matter unless you know what it is. The higher, the better. We're going here from 2002 till 2024, beginning of 25. And you can see that the forecast system over those years, in this particular score, the higher the better, has improved and improved and improved. So similar to my previous slide, where I said we did a one-day forecast, now we do a 6-day forecast, we can demonstrate we have quietly and steadily improved this forecast. Why many people don't remember is quite simple, because living memory or people's memory is always not that long-term, and you may not remember a forecast which was done 20 years ago in that particular mode. So these forecasts improve. We call them improving by 1 day a decade. So every decade the forecast gets roughly 1 day better. So a forecast 10 years ago, the quality of a 5-day forecast is today the quality of a 6-day forecast. So we're getting slowly better. It hasn't just happened with ECNWF. It has happened across the globe. And here I've plotted the forecast performance of loads of different centers: the UK, Germany, the US, Canada, Japan. Random selection. Don't worry about it too much why I did that. But you sort of can see every forecast in the world has actually improved. It's not just the European Weather Center which has improved. Everybody has gone the same way. So multiple leading centers all had a forecast performance improvement. So what did happen? Machine learning happened. And machine learning, I sort of simplify what it requires. It requires a lot of data, a lot of compute, and clever algorithms and people to use all of that. We are quite fortunate that in weather forecasting, we have all of that ready. Because weather forecasting, we have for decades, for hundreds of years, we have recorded. We have created data sets which are sort of maps without any gaps across the globe and across the time. We have the perfect archive of data for machine learning. We have the best ecosystem you can think of. We have humongous amount of computing power now. I've put here the Euro HPCs, which are sort of an EU initiative to create AI and machine learning across the globe. GPUs came along, so we have that too. And we have brilliant minds. Meteorology or Earth system scientists have always been quite fortunate that we have very good people who actually can use it. So with that, we can actually create a forecast. So that's why we now have this revolution. I'm going to come back to that later. This is a sort of more detailed slide how this actually happens. We call the data that we train on, so these big maps without gaps in time and space, is called AR5. It's called a reanalysis. We're using that to train a model, and from that we do a forecast. Again, we're going very simply back to exactly the same as I had before. A lot of data, physical equations, output. It's not too dissimilar here, to be fair, in the grand scheme of things. You have a lot of data, you train a model on that, creates a forecast. So exactly the same approach. And if you actually look at this forecast and compare these forecasts, it becomes really interesting. Today, if you look at a mouse, that represents my physical-based forecasting system. The number you see there is something we call system billing units. It basically means how much it costs to run on a computer. Okay? To do a single forecast every day, single trace, single forecast for 10 days, costs me 180,000 billing units. That's how much it costs me. If I run a machine learning model to do the same forecast for the same time scale in a similar resolution, it's 0.3. So machine learning models in terms of forecast mode reduce the amount of energy required by 1,000, and I can do it in 3 minutes rather than 30 minutes. So the physical-based forecast takes me 3 minutes and 30 minutes. But remember, what did I say before? We need data to train it. This is just a forecast. Training is a very different element here. And for this training, we need the elephant. And the elephant is the physical model used to generate those initial data for training. So when we say that machine learning forecasts are super cheap to run, for like the ant here, that is true, but we couldn't do it without the elephant. So physical modeling is still at the moment, up to today, we don't know about tomorrow, an integral part of forecasting. So we still need these physical equations at the moment. Sorry. This happens when you're right-handed and try to do something with the left hand. Sorry for that. ECMW has been very fortunate. Our member states, and Ireland is one of them, has been extremely supportive of us to do this journey of machine learning. In 2023, in June 23, we started a project called AIFS, which is the artificial forecasting system. So it's our forecasting model. In February 25, so that's just a few months ago, we released the first operational models. So within 2 years, a bit less than that, we were able to do this journey. So this development of machine learning models is actually extremely rapid. And you remember before when I said it takes us a long time to improve the forecast, to implement a new physical forecasting system takes me on average a year. It takes me a good year to improve the forecasting system. With machine learning, the speed was breathtaking, something which I've never seen before. I'm going to skip the next few slides. These are the technical details. I wasn't sure what the audience is. Anyway, so how does it perform? You remember my previous graph when I showed you all these physical models going up and showing you a good forecasting system. That's what you basically have here at the bottom with a big bracket. You could have physics-based forecasting models. On top, in these words called GraphCast, Aurora, AIFS, and Pangu, these are the machine learning models, and it's the skill of the machine learning models. And I would like you to focus on the gap between the machine learning models, for example, GraphCast, which is the Google DeepMind one, and the physically based models. This jump, what you see there, is nearly 20 to 40 years of development of physical-based modeling. So within a few months, not many, I could basically improve my model in a significant amount, which I've never even dreamt of in my career as working on forecasts. It's not just one model. The GraphCast one is Google, Aurora is the Microsoft one, Pangu is Huawei, and the AIFS is the ECMWF version of a machine learning model. So again, similar to global other physical models, you see their individual models. So this gap is absolutely exciting. So you can see why I feel this is one of the revolutions I've never seen before. You had something a bit earlier in the career when satellites came along. We started satellite observation. There was a big jump there too, which is also quite significant and is a bit comparable to this one. So similar to shooting satellites up in space and making forecasts better, we are actually now on the same scale doing it with machine learning. So these are average scores. What I do is I take the entire globe, I take measurements across the globe or parts of the globe and calculate averages. They don't mean necessarily much for extreme events. So I thought I'll go through a few extreme events for you to show you what I do there. And the first one is a tropical cyclone called Lady. I hope I pronounced this correctly, in the Indian Ocean. Some of you may remember, it was a really interesting one, to be fair. What you have here is different forecasting systems. In blue, you have the physical models. The black line is the observations, and all the other lines are machine learning models. And you can see that actually machine learning models are quite close to the physical modeling. I can go further through time. And even further through time, I realized actually it's not too bad. So the machine learning models don't actually perform just on average. They also do extremely well on track of tropical cyclones. They don't do so well yet on intensity, okay, on the strength of a tropical cyclone. But I do quite well. Another picture, you're probably quite familiar with this one. This happened here, of course, in Ireland in January 25. It was an extremely good forecast. The warnings were extremely well done by Met-Erin at this time. They were based on a physically based forecasting system. What you see here, on the left-hand side, you see the analysis, which are the observations. You've got a physics model in the middle, and then you've got the artificial intelligence model on the right. We show different variables there, but what really matters is that the AIFS, or the machine learning model, does very similar in terms of how the structure looks like compared to the physical model. Again, it doesn't do the same intensity. That has to do with resolution, slightly different issue. But again, it shows for another case study that we can actually use machine learning models in sort of real-time situations for warning. So all the skill I've showed you before, which sort of is important for forecasting, and sort of important to get the warnings out, is actually there. One more event, just to get home the point. This is a forecast. I was earlier the year in New Orleans. There was something called the American Meteorological Society meeting. The week after that, there was a severe snowstorm in New Orleans. I have to admit, I looked at the forecast the week before and I said, it's never going to happen. That must be just a wrong forecast, because these snow events usually don't tend to happen in that area. It was not really in the observed record. But if we actually look again at the forecast of the IFS and the AIFS, the machine learning model did quite well. And that is although the machine learning model has never seen that at that location in the data. So by pure transposing it across the globe, learning it from somewhere else, like physical equations, it was able to reproduce that forecast. An extreme event, as I said. So here's the thing. I can talk to you about ages and show you great case studies. I can tell you the scores went up. I can show you nice events and whatever. And you rightfully could challenge me, so I don't believe you. Where does it work? Where does it not work? Because it doesn't always work. Obviously it doesn't. And that's, I think, where transparency comes in. At the European Weather Centre, we've taken a very early step to publish those forecasts on the public web. Nowadays, you get a lot of those type of PR messages where somebody claims they have the best forecast in the world. And they may well have the best forecast in the world. I don't know. But I can't tell you, I can't prove it to you. What I can do is make the data available to you, and you can check for yourself, is it really the case? So on the ECMW websites, you find currently 6, I'm missing one here, doesn't matter which one, 6 different machine learning models next to physically based models. So if you're interested in meteorology, maybe a bit nerdy, interested to see what the weather looks like in the future, it's not really made for the general public, to be fair. I think it's more an expert audience, which we're aiming for here. You can actually go and do these forecasts and look at the pictures of them, even today. So you could go on the website now, and you could check, how does Dublin look like if I use the Microsoft forecast for tomorrow, or the NVIDIA one, or the Google one, or the Huawei one, or the ECMWF one, or actually a few other ones in that case. So you can check this out for yourself. This is because I fundamentally believe transparency in forecasting is extremely important. And transparency in showing data and showing results is key to ensure that our forecasts can be used and can be trusted for when you actually need to take actions from them. You can go one step further. You can go home, sit down on your computer. If you have a reasonably good gaming computer, so if you can play Fortnite on it, for example, then you can run your own machine learning model, okay? You need a good graphics card. But otherwise, you can download the code, you can actually install the code, you can run the code, you can optimize the code, and bam, tomorrow you're going to have your own private, personal forecast on X or LinkedIn or whatever you want to do. You can become your own weather forecast producer. The software which we use for that is Anemoy. And Anemoy is this new approach really in Europe where we all European weather services got together and worked together on one single software framework to improve weather forecasting across the globe. I think it's absolutely fantastic. And I do mean when I say you can do this in the bedroom. It's not very complicated. You need a bit of Python skills, but even there, actually, you sort of, it's quite easy. What you see here is a forecast in action developed by Met Norway, where they did a high-resolution forecast over their domain and sort of produce a forecast every day in their forecasting chain. This is actually quite exciting. Some of you may know the Norwegian weather app. It's called Year.no. And that weather app will in the future actually include that machine learning forecast. They have the first prototypes running. So machine learning forecasts are not just theoretical anymore. They're actually entering your life already, even if you don't really know it. That wasn't enough for me, I have to admit. One of the things which I always felt was quite important is to have documentation out there. So the code is something called Hugging Face. Again, ignore the details. But it sort of made the running of the forecast even easier. I said before, you need to install in your computer and your machine. Here you still need to install something, but it became even easier. So what changed was not just for the machine learning revolution that we can do better forecasts, but also that nearly anybody can nowadays run a forecast. Anybody in this room could produce a forecast tomorrow. So you could have, I don't know how many people there are, 60, 70? Can't remember. You could have 70 different forecasts tomorrow morning from each of you. And they might be slightly different because you're going to do things slightly differently. And I'm going to, upside down. I'm not good. I'm going to skip this slide. So far, I've talked about weather. I like weather, obviously. The institution I work for sort of makes that part of my DNA. It's part of my working contract, probably. However, some of you may know I'm actually a background hydrologist. I did flood forecasting for a long time in my life. So I do care about the rest of the earth too, quite a lot, and I know so do many others. If you read the latest Met-Aaron strategy, you see in there, for example, flood forecasting very explicitly mentioned, as well as many other elements. So the rest of the world is important too, not just the weather forecasting. So we went one step further now, and we're trying to include other components of the Earth system, land, ocean, sea ice, wave, and hydrology, into the same forecasting model. So the revolution is not just weather forecasting. The revolution will go to loads of other elements of the Earth system. It's funded by something called Destination Earth. Don't worry if you don't know about it. I don't know what I'm doing today. And these are the first prototypes. We started this journey maybe 8 months ago. And I can already show you now forecasts for ocean, land, and sea ice within the last 8 months, which have comparable quality, not better yet, to be important, than what we have otherwise. So we can actually use these machine learning models and forecasts far beyond weather. Weather is just one of the many applications of the Earth system forecasting how we're going to use this. And that's not it. We also work in the areas of climate and climate modeling. Climate change is obviously a big topic. There's a lot of questions how weather looks in the future and how would weather look like if you sort of do it with a climate. And climate models are extremely expensive to run. They're they're marvelous pieces of technology. They really contain the amount of knowledge which is in these lines of codes is tremendously and is really impressive. But they are expensive to run, they're difficult to run, they're complicated to run. So nowadays we work on something to try to emulate those climate forecasts, trying to make those climate forecasts better. And on the left-hand side, you see actually a slightly different side project. What we try to do is simulate what the weather forecast would look like in a changing climate. So we try to use a weather forecast model of today, we use the changing climate, and we wanted to see how the weather forecast would change given that changing climate. The results are currently not there, they're not brilliant yet, but the progress again is quite amazing. And that's not it. The problem with machine learning, there's always something else which comes. There's always something else which sort of gives. With machine learning, I sort of said to you earlier, you can go home and do that yourself. What do you think that means for the world? What do you think that means for countries where the infrastructure is less strong, where the technology is less sort of embedded in society for doing weather forecasts? What does it mean for small island states who currently couldn't afford to run a weather forecast? It's democratizing forecasting as such. It will allow anybody, any agency, any member of the World Meteorological Organization, any national hydrometeorological service to produce their own forecast, to own their forecast, to issue their own forecast, to be really theirs. We did have this in the past. We used something called limited area models, and they were hugely successful. They were successful, but they were quite difficult. This is going to be easy. We use something called a system called forecast in a box. It's basically that. I sort of told you before that you have to install that thing yourself still. This system makes it even more automatic. You may have seen there was an announcement by NVIDIA about a forecast, which sort of was a desktop type station, and you could pre-install that on there, and they could just run the forecast for their domain, however they like, or in a cloud environment or whatever. So the tremendous change of this machine learning and weather forecasting is not just going to be that the scores, the forecasts are better. It's going to be that anybody can use it, and every world will have their own early warning system for weather and climate. The dream that we can really, that any country can protect themselves, can protect their citizens, can protect lives and livelihoods, is possible through this in a fairly low cost. It's still not super easy. So now there comes the crossover. I'm not sure how many of you have used ChatGPT or the likes for it. Quite a few probably. I quite like it. I like it to do summaries of important papers. Don't quote me on this one. They're quite good actually, with these summaries. Anyway, what we wanted to do is go one step further. We wanted to really interact with the data. You've seen my maps. My maps are very technical. They're not really accessible to the wider public. They're quite difficult to interact with. The data formats we use are horrendously complicated. Okay? They're not fun, to be honest. You sometimes spend longer in trying to decode data than you actually look at analyzing data if you're unlucky. So we are working on something called a climate and weather chatbot, which allows you to question the data, allows you to interact with the data. And the example, which I don't know whether it's going to work, I have here, for example, is planting an olive producing trees in Bavaria. That's where I come from. I quite like olive oil. So that's how we got to that example, fairly simple, sorry for that. We are trying to see, under a changing climate, will it ever be possible to plant olive trees in that particular climate? It analyzes the data, it looks at local soil types, and sort of gives you a first hint of whether maybe I can grow olives in my tiny little village near the mountains. I will, probably. I still need an expert to have an interpretation of that. That is just a first shot. This is not good enough for you making a decision. Okay? So it's more than that. This machine learning will not only make your forecasts better, will give you earlier warnings, will democratize it and make it available to everybody. You will also be able to really interact with those data. You will be able to question those data. Rather than having a pre-made app or a pre-made display for you, you can really say, So how is the temperature in Dublin going to look like in 2050? What does this mean for my building codes? And with the right interactions, you could get to that stage. That's a still bit future music, but I think we're not far off. Criticism. It's not the greatest of all. Okay, machine learning does have its problems. And I sort of listed here a few. Lack of physical understanding. Physics is hugely important. We created physical equations for hundreds, thousands of years. They are based on knowledge, they're based on observations, they're really extremely valuable. We put a lot of effort as humanity into creating this physics in there. We need physical understanding in that model. I give you a very simple example. Machine learning models can produce negative precipitation, negative rainfall. We sort of heard about evaporation. That's not really what's meant here. It's really negative rainfall because machine learning models don't care about physics unless you tell them to care about physics. So our latest model, for example, prevents negative precipitation to be created, but we have to put this in. This physical understanding has to be put in. It's a very simple example. You can make this example far more complex in terms of physics. You're going to get there and you sort of have hybrid models and you've got data-driven models. On the right-hand side, I've put on whether this already applies to existing models. And surprisingly, maybe to some of you, even our physics models are an interpretation or a sort of an abstract framework of our equations put into real code and sort of therefore have a translation issue, do sometimes create unphysical situations. It happens in physical models too. It's sometimes a bit less likely. Extremes, I've showed you some extremes where it worked, but there's also an issue, of course. A lot of the extreme weather we are seeing hasn't necessarily been recorded or seen in our lifetime or even been ever on record. I've sort of shown you the example of the snowfall where this worked. I can show you some other examples, but there's definitely a concern that if you ignore physics, where it's far easier to extrapolate, that with machine learning you may not be able to do that. Again, it does happen in physical models too, but to a lesser extent. Massive training data. You need huge amounts of data. Weather forecasting always needs huge amount of data. We always want more data. We are an extremely data-hungry discipline. The more you give us, the more we're going to gobble up and use. So it's extremely important for us. Uncertainty, I sort of haven't shown you any uncertain forecast. Weather forecasts are uncertain. The European Weather Centre doesn't just produce one future, it produces 51 futures. So we don't just give you the forecast for tomorrow as one single number, we give you 51 different scenarios of that future. And the reason is the weather is uncertain, the atmosphere is uncertain, the initial conditions are uncertain. We don't always know everything exactly. So the future is uncertain, and we forecast that uncertain future with physically based models. Machine learning models, not yet. We're having our first version. We will have our first shot at that in June, July this year. What else do I pick out there? I'm going to go a bit to the bottom. The rest is less interesting. Overhyped in the media. There's no question that machine learning and AI currently receives a lot of attention, and it's quite clearly that it very often receives very positive attention in many respects. One has to be extremely careful, and that goes back to my argument of transparency, that not everything which sort of is in a press release is really necessarily the entire truth. I'm not saying it's untrue, I'm just saying it's sometimes very selective in that sense. We did have that with physical models too. Okay, this is not just a machine learning model, it's actually quite abstract. And then the two other elements is high energy costs. Machine learning models take a lot of energy to train, a huge amount of energy. I need a supercomputer to train a machine learning model. You've seen sort of the costs for training ChatGPT. Big data centers are now very, very often built next to power stations, renewable energy stations, or anything else, because they need so much energy to run those computers. It's a huge cost. And here comes my but. I've done the same with my physical-based models. To develop and release a new physical-based model, as I said before, it takes me a year. A year of over 100 scientists, a year of a supercomputer, a year of endless rerunning, recoding, retrying, experimenting. So I'm already today in the weather forecasting business. I would argue we overuse that energy anyway. So it's not too different in terms of for the machine learning. And the last point for me is actually quite an important one. I've shown you very short-range forecasts here. Most of my forecasts were under 10 days. Some of them were 14 days. The real challenge we currently have in meteorology is the predictability barrier, which is sort of 2 to 3 weeks out, depending on the variable you look at, sometimes a bit longer. It depends a bit. So for the surface variables. We have a problem that we have advanced the forecasting in this area, but not really dramatically. So the graphs I've shown you of curves going up, I couldn't really show you a similar gradient for forecasts for week 2 and 3. If we really want to prepare for more extreme weather in a changing climate, we need those forecasts. We desperately need those forecasts. So we need to break this barrier of predictability in machine learning, but also in physical forecasting. To do so, we have created an AI weather quest. I've said to you, you can run your own forecast model in your bedroom tonight. And now I challenge you. Take that forecast model and take part in that competition. Show the world that you can do better than anybody else. Show that your model, which you've just created on your Fortnite computer, is actually better than anybody else. So we are really throwing it out here. I would like to see any of you trying out. We have at the moment 73 teams registered, which is quite a lot, more than I was expecting. And 79 models are taking part in this competition. It sort of illustrates two things. It illustrates my point that this is really still the barrier of forecasting. It's extremely important that we're sort of all trying to do it, but also that many people actually think they can do it. So you can run your own forecast. You can produce your own forecast. Then you can take part in this challenge. I'm really sorry, there's no prize money. All you get is probably a handshake in a nice certificate. That's all we can offer. No money, sorry. Anyway, so my 3 messages I hope I got across to you before is one of the most important ones. We are still just scratching the surface. We haven't really gone through the full cycle of revolution yet. We haven't really hit that plateau yet. We haven't really hit that area where we say, oh, we don't get any more improvements from machine learning. We are at the moment still far off that. And even in terms of applications, we haven't even yet scratched the surface. I talked a lot about forecasting. Running a weather forecast as a service or as a center or as an organization involves far more than that. You need to translate that forecast into warnings. You need to clean up the observations. There's many other aspects in weather forecasting which sort of are going to be touched by machine learning, but are just in the infancy of that. It will transform the weather forecasting business. It will transform your lives, your personal lives. The machine learning forecasts are more accurate than traditional forecasts, and machine learning applications, even if my title was about the weather, goes significantly beyond weather. It will be touching every single other hazard forecast you can think of. If you see a forecast, it will be influenced by machine learning in some shape or form. And that's all I had. Thank you very much.
Brilliant. Thanks, Florian. That was great. I'm used to having slides when I give talks, so this is a new experience for me. So I've gone very old school, so I have notes on pen and paper here. But I will be using Florian's slides to illustrate some of the points that occurred to me when I was looking at this. So to start off, it's brilliant to be here. Love this room, love the RIA. It's such a great place, and very exciting to be part of this evening's event. Thanks very much, Florian, for doing a brilliant presentation and pretty much for doing my job, because as respondent, I need to have some ideas about questions I can raise, and I think Florian's already raised most of them, but I'll still go back maybe and highlight some of these. Part of the idea of the respondent's role, I think, is to get us going with the Q&A, but the audience here is so exceptional that I think, again, my job's already been done for me, so I have quite an easy one here. So I'm going to go through it sequentially and just talk about some ideas that occurred to me while I was looking through Florian's talk, which he kindly shared with me before this evening. So first, I was thinking about AI, and I was talking to people I knew about AI, not necessarily weather geeks, which maybe all of us are, but just other people, anyone. We had an interesting talk before we kicked off this evening about people who work in creativity and their fears about AI. And I think it's kind of interesting to put it in the context of some of the things that can happen. I'm an academic, work in UCD. A few people here are academics. I think there's a large discussion around the use of AI and plagiarism, which is kind of an interesting risk that we have to face. People are talking about it transforming, I think, many aspects of society. With that come, I guess, questions about fears over job security. Will you have your job? Will that be transformed? What's going to happen to you in the future? And then there's maybe getting a little bit broader concerns around fake news. Recent elections have shown the power of fake news and misinformation on society. Is AI going to take that to a whole new level? And then finally, I'll come to the positive points in a minute, but one of the big concerns that occurred to me weren't really any of those. I must say, overall, I'm very optimistic about AI, and I think it has amazing power, and it will lead to amazing good things in the future. The one concern I would raise, though, is who owns AI? Who regulates AI? It will be very powerful, but there is a fear that the power will be controlled by a smaller and smaller number of people. And I think the regulation of AI is a very important part of what we're facing into, because I completely believe it is going to transform the business that we're in. But to move on to a positive note, this evening we're here to talk about AI and weather forecasting, or meteorology and climate. And I really think it's going to be a massive power for good in the area that we work in. I'm very excited about the things that Florian has shared with us this evening. It's happening so quickly that at times it's like I'm living through a sci-fi movie. You know, I'm not sure if it's Star Trek or if it's Alien, but hopefully it's a nice future and not a despondent future. But AI is definitely going to be stepping up in ways that we couldn't have considered would happen very recently, just over a decade ago. I love this slide. Professor Peter Lynch, who I see in the audience, wrote a book about Richardson and included this image in it. And it's great. It's so far-reaching. It's full of so much foresight. And as Florian said, this is what high-performance computing does. This is how we produce our forecasts today. And it's based on a good understanding of the physical laws of the atmosphere, which took humans centuries to get to. Now, I think that's a really interesting point. So it took us centuries to come up with why the apple falls and to describe that in the language of mathematics and to put that into a computer. Now, what AI does is it looks at all these observations. And as Florian hinted, it kind of comes up with its own laws of physics. They're not our laws of physics, but it is coming up with a relationship between massive amounts of data on the one hand and observations on the other hand. And I think it's almost like aliens landing and coming up with a whole new branch of physics and saying, look, this is what we think. And so it's tricky because we don't really speak their language, but it's full of great potential because I think they will offer insights for us that our centuries of observations have not provided us with yet. There are obviously things we're not doing right if AI is outperforming us. And I think this gives us great opportunities to move in that direction. Okay, let's go on to the revolutions. So that phrase, the quiet revolution, in the increase in skill. So we see that the skill has gone up over time, and this, we've had loads of revolutions over time. We've survived them all. There's the printing press, there's arguably bicycles, there's the typing pool and word processors, there's the internet, whatever, loads of revolutions, loads of things that people would have thought were going to transform society. And I mean, a lot of them did. But I think humans are very good at making the most of these opportunities. So I, again, see AI as a revolution. It's certainly not a quiet one. It's a very noisy one. But I also think it's a revolution that we can come out with really, really good new knowledge from. Now, part of what I need to do, I think, is raise some questions. So one of them, I guess one of the main things that occurs to me about the status of AI for forecasting at the moment is the fact that we do have lots and lots of data that we're feeding in. But the data comes from the analysis. Largely, tonight we're talking about era 5. And there's a great phrase in mathematical modeling, garbage in equals garbage out. I'm absolutely not saying era 5 is garbage, but there are well-known biases and unknowns within the data that we're using to train these forecasts. And it's going to be very difficult for the forecasts to figure out what the truth is if the data we're training it is not the truth. So reanalysis are not actually the truth, and they miss a lot of things themselves. And so I think that will largely limit where we go. As an example is parameterizations, which are bits that the computer doesn't completely solve the governing equations for. Things like turbulence and microphysics for clouds. Clouds are really interesting, quite complicated. So our physical models don't get them right. So therefore the reanalysis doesn't get them right, which means it's very unlikely the AI is going to get them right. Of course, on the flip side, this could be a great opportunity for us to use AI to try and improve the areas of physics that we currently aren't very good at. And that's part of my belief of AI being a tool for good. Florian also mentioned on the TC, I think that's really interesting, the tropical cyclones. It's really good at tracks. It's not really good at intensity. So it doesn't get the max wind speeds, I mean, give or take, it doesn't really get the max wind speeds right. We even saw that briefly on the storm Eowyn plot, where it got what we call the synoptic structure, the shape of the storm was well represented, but the intensity, the max wind speed wasn't. That could be related to the training that they're using in AIFS, where they have this cost loss operational optimization thing. They need to make the areas smaller and smaller and smaller. That involves a certain amount of smoothing, which may inherently link the ability of AI, at the moment anyway, to capture some of these extreme events. But again, that comes with an advantage. So AI is not constrained by the laws of physics. And one of the ideas about why AI does so well with tropical cyclone tracks is because it's kind of looked at lots of pictures. It's gone, this is what happened, this is what happened, this is what happened, this is what happened. It's brilliant at spatial recognition. And spatial recognition is really tricky. Humans are brilliant at spatial recognition. Until recently, machines really weren't. So when an AI is making a forecast, it's taking the pattern into account. NWP only solves the laws of physics. It explicitly does not take the patterns into account. And one of the theories is that by taking the pattern into account, that's why the TC tracks are better than the physics, because it's a different way of solving the problem. So again, a really interesting future, and I think a lot of potential there. It does raise a question. Florian said that his background is in hydrology and flood forecasting. Oh, wait, now where am I? I think I've gone past it. Oh, no, I haven't. Yeah, these are the extremes. Great. I've talked about the extremes. So with flood forecasting, a lot of it involves what are called compound events. So let's say there's lots of rain and there's also wind pushing the sea onshore and there's a high tide. So the wind and the sea level and the rain all combine and then basements flood in Cork or whatever happens. But that involves knowing at the same time what's happening with all those different variables. And I'd be interested if AI is able to handle that kind of compound event, maybe as well as the physics models, where it's really built into it. Then this slide, I think this is great. I think it's amazing what the ECMWF are doing for AI. They're really democratizing everything. So they've got these leading AI models that we can look at. We, scientists or weather nerds or whatever, we can see the best that's out there and we can play around with it. And I think a really interesting aspect of this is the scores that Florian has shown us. So things like anomaly correlation coefficient scores that are familiar for people in meteorology, but maybe don't cover what you're interested in. By giving us access to the models and the data, you can use your own skill scores and you can decide for yourself where it has strengths and where it has weaknesses. And I think that's a very exciting thing to do. And I think it's fantastic that they've opened up the existing models and their own online models so that enthusiasts and not just specialists can get involved. And the competition that you mentioned at the end is a great opportunity for us to get input from so many different aspects of backgrounds. I'm going to go on then, mention briefly, oh, I love this, he skipped this. This is really exciting, going straight from observations to the forecast without doing lots of the stuff in the middle, but we won't get into that now. I want to briefly mention two more things before I wrap up. One of them is ocean modeling. I hadn't known that it had been applied for Destination Earth. Really amazing model of the entire globe. The EU wants to develop a digital twin of the planet that we live on and get the best science into it. The ocean modeling aspect of this, I think is really ambitious. It's great to see people tackling this. The ocean is kind of one of the great unknowns for us. We can see the atmosphere, we can see the land, we can't really see very deep into the ocean. And the ocean is deeper than Everest is high. And the overturning circulation, how quickly the water at the top changes with the water at the bottom of the ocean, takes centuries. So this is a really, really tricky problem. And we have very little data. So it'll be really interesting to see how AI manages to handle something as kind of fiendishly complex as this. And as if that wasn't bad enough, Florian went on to mention climate models. So climate models are amazing, fiendishly complex even within the physics side of things. Loads of uncertainty, very tricky to analyze and to run and to compare. And so the idea of using AI for this is a brilliant opportunity because these are extremely computationally expensive models. But it's extremely challenging. So if we think back to the idea, Florian explained it very well, AI is built on data. And the data here is Era 5, and Era 5 is the past. Climate models are based on physics, and they want to try and project what will happen, usually by the end of the century, up to the year 2100. To do that, by definition, involves moving away from your training data. There's something that's kind of based a little bit on the idea of chaos. There's a Lorentz attractor. You might have seen this pretty shape of a kind of a butterfly or an owl mask. Weather will always be within that owl mask. Climate change changes the shape of the owl mask. The entire climate will change. And for AI to go beyond anything it has ever seen in a climate that did not exist will be really, really interesting and I think quite challenging to see. Brilliant. So I just want to agree with a number of points that Florian mentioned here. First of all, well, thanks for doing my job for me. It's a great list of strengths and weaknesses. I want to summarize some that really struck me. The strengths, it's really efficient, it's really rapid. We can run multiple runs, which will, amongst other things, actually be environmentally friendly and reduce greenhouse gas emissions. AI is excellent for pattern recognition, the spatial aspect, like I mentioned earlier with the topic cycling tracks. I think that's a really interesting aspect of how AI works, and I think it could bring us back to new insights into data. At the moment, we use things like the El Nino or La Nina or the North Atlantic Oscillation. You may have heard of these terms. There are spatial patterns, but our models don't care because they're just based on the laws of physics, whereas AI kind of does care, which gives us a new insight. And by coupling AI with our physics, I really think we can unlock deeper insights into the future. The problems then, I think one of them certainly is uncertainty. It's a great AIFS model that's been developed, but with the physics ones, we know exactly why they're different. It again goes back to chaos theory and Tim Palmer, who did amazing work in ECMWF on this. And so when we have uncertainty from physics, we know why there's uncertainty. We're not really able to interpret why AI has that uncertainty. And that comes on to really the point I want to finish on, which I think may be front and center of all the national med agencies, which is accountability. You have a forecast, the forecast is great. It's better than the one that you understand. So everyone starts using it and everyone starts demanding it. But as a med agency, you're responsible to the people of the state. If you use a forecast that you don't understand but is better than your forecast, people are happy until it goes wrong. If you don't forecast an event that does happen or forecast an event that doesn't happen, at the moment we can say why. With AI, we can't. And that is a real counterbalance to the many advantages, I think, that we see with AI in this world. So to finish off, and maybe to go back to the quiet revolution phrase, I think that human expertise will always need to be included in this loop. I think AI will be a tool that should be run as well as physics, which Florian has highlighted here. But I think maybe we should keep part of this revolution a little bit quiet and keep the decadal progress in the physics-based science going on hand in hand with AI. Thank you very much.
So our current models don't include meteorites, to be fair, so they're not included in our forecasting model. I think there's a sort of an interesting question there, because Let's go away from meteorites, which sort of destroy the planet, and think of volcanoes, which are sort of a very similar issue. A large volcano nowadays will change the climate quite significantly. And even they are not really in our weather forecasting models. We simulate them a bit in other type of models, but I think it's not the same extent. So it's a very valid question, maybe not meteorites, but similar disaster type of events. And they're not really included in physical models, included in some climate change simulations, but not really in weather forecasting type of situations. If we have a volcano outbreak, we usually have to inject that by hand into the model, and that more or less mean that we have to rerun the model and simulate the particles in the atmosphere to do so. We can't really forecast those events, or at least to my knowledge, forecast those events to an accuracy which would be comparable to a weather forecasting model.
I'll say something on it. Yes, absolutely. I think explainable AI is a very strong tool in the toolbox that faces us ahead. There are a number of different approaches to explainable AI, but I know a number of people in Europe that are already using it in meteorology. I think particularly to try and investigate this idea of seamless forecasting, where you go from forecasting from days to weeks to maybe months. And the feeling is that we can learn a lot about improving the skill of physical models by using explainable AI for those. I don't know if you...
No, it's a perfect answer. I think the only thing I sort of would add that very often weather forecasting, how we explain the weather is by looking at the output maps. That sort of is very similar to what we would do in a physical type model in that sense. But I think AI in the future will be able to guide us better to find the right maps and structures we have to. So it's a bit of a different take on explainable AI as such. But physics informed AI, or however it's termed quite differently nowadays, is becoming a far more popular thing. And I sort of explained before that we sort of now train the loss function to ensure it doesn't produce negative precipitation. And we make this far more complex now. And that sort of is going in the same direction in that way. So we're sort of trying to put in physics basic understanding, and therefore have some explainable of the AI structures in there. But I think Conor was putting it quite rightly. There is a bit of an issue that we can't really explain everything. And sometimes we don't really know why things go wrong or right. So there is this fact that our supercomputer produces huge amounts of carbon. It's an expensive, energy-hungry operation. To produce a forecast is damaging to the climate, is damaging to our world. There's no question about that. As I sort of try to allude that for weather forecasting, rather than doing it generally, I think the problem is the same. So we currently, our physical models run on the same, or not the same, a similar type of computing infrastructure. So our current models are already polluting the climate. Let's put it in those general terms. Which sort of gives us already the obligation now to see how we can make this more energy efficient and how we can make this easier. And I think there actually AI has probably a greater potential to reduce energy consumption and therefore reduce the climate impact than maybe our current physical models have. I think it's early days, but yes, the data centers do impact the climate, and it is in our responsibility to reduce that impact. I'm not going to talk about the general data centers because I know less about it. It's quite an interesting question. Okay, I would add to better computers to your list, so better data, better models, and better computing. If you look at the past, so let's forget AI for a moment and look at the improvements of weather forecasting as such. About 50% of the improvements come from something called data assimilation, and 50% come from other sources. So it sort of is both of it. So my answer to your question would be, it is both of it. It is data where we currently lack data, so data poor regions. You mentioned the ocean. if we would have suddenly a perfect observation of the entire ocean, I'm sure we could make a jump in performance of forecasting the ocean. But it is more than that. And I'm going back to what Conor said about humans. It is also the human brains required and the human intelligence required to actually improve that. So it is all of that, and I wouldn't really put it down to a single data source or a single answer. However, collecting data is hugely expensive, is hugely important, it's hugely expensive, and it's extremely important that we keep investing into national data infrastructures to collect those data. Without those data, we can do nothing.
I might add something to that. I mean, I completely agree. But I think another thing might be that we're better at using the data we have. Although you use 800 million data points in data assimilation, we're not using all the data we have. There's lots of data from satellites that we're not using at all in our physical-based models because there's just too much. So AI, again, offers a great opportunity to highlight the best return on investment for new observations, but also the best use of existing observations, I think. I'll give the quick answer, and Florian can get the intelligent answer. The quick answer is yes, absolutely. So we reforecast historical events to learn more about what happened and the sensitivity to particular observations. I think going back further, there was Storm Lothar, which was completely wrong because of the lack of one observation, which is out in the sea. So we do run things again to learn. Now again, AI is a great tool here. So a paper that you just flagged recently that's in arXiv has shown the use of AI to change the ERA 5 data to result in much better forecasts. So almost AI is looking at where ERA 5 has gone wrong and then adjusting it slightly to produce better forecasts.
I'm going to ask you a very simple question. When you looked at the weather forecast, did you look where it was coming from? The current weather forecast on your app. I think what I'm trying to illustrate is that even now you have an over-reliance on something. You're not entirely sure what it really is. So it's not really that just an AI problem. I think it's maybe more a general problem we have at the moment that this is so complex. Large language models do pose an additional challenge. And I did say you need still an expert in the room. Well, I didn't use that word, I think, this time. When you do my olive tree type of example, it's not just something you can just do and use like this. However, for the first time, you have access to this information rather than having to go to some complicated loop, which you would never do. So yes, there's a real problem. There's a real problem of over-reliance on these outputs, and there's a real problem of people taking them as a truth. But we do have this today too, and I think this is where people who really do weather forecasts or make interpretation of weather forecasts, like Met-Arian, who are national institutions who know the weather, are so vital and so important to translate this information to something and sort of make the right interpretations for everybody to allow the right decisions. So yes, we are, but I think we have the mechanisms in place to actually deal with that. And our national hydrometeorological services are the gold standard for actually doing that type of interpretation. I'm going to start and maybe I'll let you finish off. The short answer is yes. As I said, everybody in this room can do a weather forecast. That may be 59 wrong forecasts, okay, and one right forecast. This democratization of forecasting comes at a cost. However, I'm sort of going back to what I tried to say before. We do have institutions which are vetted, which have the infrastructure, which have the trust, which have the knowledge, who are working together in the World Meteorological Organization to really show that we can do that type of interpretation. I'm sort of aware it doesn't entirely protect everybody because there may well be a notification on your phone turning up and you don't know really where it comes from. And I think this is why it so becomes important to go back to what is the real authoritative voice, who's the trusted voice, who can really issue these warnings. I think just in this age of where we get loads of different informations, and I don't think it's just weather forecasting, We need to really work hard on establishing what are the trusted sources for that. So forecasts are used for critical infrastructure and electricity transmission and distribution, and are actually used quite successfully. We have great examples for renewable energies, but also for large distributors. Spain. All I can say that I have no evidence in the data that the weather was in any way unusual to what it usually would have been this time around of the year. The fluctuations were what you would observe normally within the climate variations. So I find it very difficult to make the link, but I don't know, between that weather pattern and necessarily the impact. The data do not support it being unusual.
Might make a quick follow-on to that, because I do some research with renewable energy, and a friend of mine in UCD is a power systems engineer. And when I saw this on, I think, was it Monday, it all kicked off, and I WhatsApped him saying, what the hell's going on with the power system? And he WhatsApped back saying, it's not our fault, it's your fault. So at the moment, I think we need to wait to find out exactly what happened. Nobody's really taking ownership, so I will be as curious to you as you are to see what the answer is. But maybe an example closer to home, and Med Éireann may hate me saying this, but 25.9 degrees in Athenry yesterday is a new record for the month that we're in. I had a quick look at the IFS and the AIFS, so the physics-based model and the AI-based model for Athenry. A week ago, the physics-based model said the temperatures would go up to, it's a whole collection of models, but the highest of any of them was 21 degrees. And it said that a week in advance, and it said the same thing one day in advance. The AI model had its highest temperature as 24 degrees, which is significantly closer to the temperature that we actually observed. Now, I wouldn't draw any conclusions from that. But to answer your question, I guess the AI can handle these kind of extremes, sometimes in situations where even the physics ones don't.
I think that's a great question. Urban forecasting is super interesting. I'm mainly working on the health aspect there. And we are currently using AI to improve heat health forecasting for urban areas. I know this is only one aspect of urban, sort of whereas it's a very small one. And the machine learning models we are currently applying that do better than the physical models we are having. Having said that, there have been, as you know probably yourself, loads of different studies comparing different ways of doing urban forecasting. And the most complex ones have not always outperformed the simpler physical ones, to be fair. So I think it's actually one of those areas where I'm going back to what Conor said. AI may teach us something about the physics which we may not have fully understood yet. Usually you've got quite good data for many urban areas, to be fair. And actually may advance our physical understanding more than many other areas. So I think there's a great potential. We are currently working for an application in Valencia in heat health. And there the heat health is better with the AI than the physical one. But I'm not entirely sure this is entirely due to the physical model. I'm sort of I'm still thinking we don't understand the physics 100%, or we don't represent the physics 100%, or something thereof. That would be sort of my interpretation of it. It's very much the same as weather forecasting, to be fair, in terms of human health impacting. We also use human health. Human health is a bit more complicated, particularly when we talk about urban areas, and we're talking about indoors and outdoors, and we're talking about air quality on top of that. So it's sort of a very quite interesting component. But we do have fairly a lot of data-rich areas, or some data-rich areas, maybe less the ones you just mentioned, to be really fair, where we have data to optimize models. If you go in the area of air quality, for example, there is undoubtedly currently a challenge in our current air quality forecasts in how expensive they are to run in a real forecasting type of environment. We are running a global air quality forecast. It's a very, compared to our normal weather forecast, it's a very coarse resolution. It's a very large grid, because forecasting the how do I put this in terms now, the chemistry of the Earth, or the chemistry of the weather, is extremely expensive to model. And I think AI and machine learning will take that expense out, and therefore may allow us to do higher resolution, smaller scale forecasts than we are currently even physically possible on the biggest computer. So there's an opportunity there. If you talk about human health impact, I'm sort of slightly less confident, because the data are far more difficult to use, but you probably know this better than me, to be fair, in this area. So I think there's an issue about data quality, which comes in and starts to limit the use for ML and AI quite quickly. So that's a bit of my concern in that. It's a great point. I think it's also about using energy at the right time. So using energy when maybe it's used less and sort of would be cheaper to use, like what we currently do at night with some of our, I don't know how it is in Ireland, but some of our terraces are like this, for example. Yes, there are. I actually just recently looked at a quote for my roof for new solar panels, and there's now apps out there which allow you to sort of optimize the energy usage given the weather forecast. And I only need solar radiation, a bit of other stuff, to do a good forecast for energy production for my house. I don't need those 800 million data. I need a really tiny fraction of that, maybe 10, let's be fair. And yes, they exist and they already have an impact. And if you look very closely, some of the car manufacturers do the similar thing. Actually, they're trying to forecast the energy availability to the grid, and therefore allow you to charge your car at the right times. So there's an impact which is also slowly coming. It's very often weather related, and you see this in sort of auxiliary apps already. ECMWF still distributes a lot of its forecast to commercial customers or to commercial entities, and it's a huge variety of interesting applications. Building control with weather forecasts is a very popular thing. So when do you put the blinds down? When do you put the blinds up? To simplify it now, in a way. So that is a huge application. That's where AI and ML actually works quite well, because you do have to tend data in a very small scale, but you have to tend to have very good data, and you don't need much else, as you said. You don't need the 800 million. 10 is enough. But they exist, and I'm quite amazed how quickly that field moves. I'm impressed. I love it. Anyway.
Great, so perhaps we'll leave it there, and on behalf of the Academy, could you please join with me in thanking Florian for a super presentation, really interesting, thought-provoking. Conor, great job as a respondent, very relaxed but to the point, well done. And to you, the audience, thanks not just for your attendance, but actually your participation as well. So it's always a good reflection of how interesting a discourse is as to just how many questions come from the floor. And I'm sure there'll be others that you can ask each other, or indeed Florian or Conor, when we have our wine reception in a little bit. It's a great end to the AI series, the 6th now, and I think it's really interesting, and we'll have a report coming through on the 6th, and then we'll have all of those put together. We'll be able to analyse just exactly where we are right now in terms of AI. So it's been a very interesting experience, I have to say, to listen to all the presentations. Some final comments, and this is particularly to the audience. You may also be interested to know that our Irish Academy Library is hosting Weathered Pages, Unveiling the Past Through Meteorological Research at the Royal Irish Academy Library, an exhibition curated by Dr. Carla Mateus, an assistant professor in the Geography Department at Maynooth University. The exhibition highlights the role of the Academy as a curator of historical meteorological records across the island of Ireland, as a publisher of diverse papers on instrumentation and meteorological observations, and also as a learned body which encouraged a standardised approach for reliable weather recording. The meteorological observations preserved in the Academy archives date from the late 18th to the mid-19th century and are of cultural and scientific importance. Such records are crucial to better access past climate variability and trends and the frequency, intensity, duration and distribution of extreme weather events, and to put the current climate change into a historical context. If you would like to join a 20-minute guided tour of the Royal Irish Academy's historical meteorological collection, tickets are available at www.ria.ie/events. And for any members of the Academy, if you haven't already done so, please sign, and I haven't myself, please sign the attendance book in the hall outside the library, please. Thank you all for attending this evening's discourse, and do please join us now for refreshments in the front rooms, and the speakers and officers will now process out ahead of the audience. Okay, thank you very much.